Now let's look at a few rate of change problems. Consider the following problem as an example of linear motion. A student walks away from the origin to a displacement of 8 meters in 10 seconds. So let's just pick our origin over here. Let's say this is our origin. So right there, origin 0. Right, and then here's our little student. And we're going to walk a displacement of 8 meters in 10 seconds. So we're going to walk 8 meters to about here. It's going to take us 10 seconds to do that. And then look what happens. The student then stands still for 10 seconds. So they're just standing there for about 10 seconds. The student walks 4 meters toward the origin in about 4 seconds. So we walk back to origin. So we're going to walk 4 meters this way. If we walk 4 meters back, so we're probably going to be at 4 meters. And that took us 4 seconds. I probably should have wrote that here instead. Then the student stands still for 6 seconds. So now we're just standing here for 6 seconds. And then lastly, the student walks away from the origin to a displacement of 14 meters in 5 seconds. So we're walking away from the origin. So we're going away from the origin, we're walking to the right. We're going to get to 14 meters in about 5 seconds. So here's 4, here's 8, 14 to be around here-ish. It's take us 8 seconds to get there. 5 seconds to get there. And then that's our little diagram of what happened in a little 2D motion. Right, that's just like a picture of what's going on. Let's look at it in a graph sense, right? So we're walking and moving around, and we're taking time to do it. So if you actually graph that, the student walks away from the origin at a displacement of 8 meters in 10 seconds. It looks like this. It's right here. If we look at it, right, we start at the origin. So actually, let's label this. This is seconds, and this is meters. So you just have some idea. So this is time in seconds, this is distance. So we start at the origin, so 0, 0. Remember what it said? It took us 10 seconds to go to 8 meters. So I should have a point of 10, 8. I should get to. So look at our graph here. You get to 10, 8. Right, so that's our first little thing. And then we have a next. Right? Students stand still for 10 seconds. So you can see that here. They just stand still for 10 seconds. They didn't move anywhere. We didn't get any further, closer away for 10 seconds. So we're at 20 seconds now, right? We're at 10 seconds for 20. Then what happened? I walk back. Student walks 4 meters toward the origin, 4 seconds. So 4 meters toward origin. So if we were at 8, we should get down to 4, as we do, and it should take us 4 seconds. So from 20 to 24. So we're all good. And then we stand still for another 6 seconds. So again, we're not moving, so we're just standing still for 6 seconds. And then finally, we race over. Student walks away from the origin to a displacement of 14 meters in 5 seconds. So you got all the way up to 14 meters, and it took us 5 seconds from where we were. So that's what the graph looks like, right? Using all the information we had. Remember, this tells you what position you're at. So how far you are from the origin at any time. That's what position graph's about. Now, if we want to find the velocity, we'll just take the derivative. So if we take a derivative of all these. Now, we know how to take a derivative of a graph. We just look at the slopes. So if I look at the slope of this guy, this is what, 10 and 8. So my slope should be 8 over 10. Or 4/5. My slope here should be 0. This one, we went from 8 to 4, so negative 4, and then it took us 4 seconds. Yeah. So that's negative 1. And then we're at 0. And the final one, we went across. Took us 4 seconds to go across, and we went up 8. So 2. Right? So if we just graph those, we get something like this. Just up before we want to label our axes. So our x here is still time. So time with seconds. So let's put little seconds here. Our y this time is velocity, so meters per second. Right? And if this follows the graph we just did. And when we first started, we're increasing our velocity. We're going faster to the positive right direction. So that's why we have a positive velocity. Then we stood still for like 10 seconds. And then we have a negative velocity here. Keep that in mind, that's not like slowing down, that's literally going the wrong direction, right? We went the opposite direction, we went back, so that's why it's a negative velocity. The sign just tells you what position you're going, which direction you're going. Then we stood still, and then we hightailed it fast opposite direction. So that's what the velocity graph of our function looks like. And it tells you in which direction are we moving at every point. So positive, still, wrong direction, opposite direction, still, positive right direction. Okay, now let's put like these into words. The basics and rates of change. So anytime you hear the words initially, so this is like the key to rates of change. It's all about memorizing these words, like this vocab, or just kind of using logic. But this is really going to be the key of all rates of change problems. So when you hear initially, or initial, that means that you just started, so that means time equals 0. So that's very important, right? So initially, initial, time, you just started, time equals 0. At the origin, that's a position question. Like, where are you at? That's position. So position, S of t generally, position. So position equals 0. So that's the original function. At rest, so what does it mean to be at rest? It means you're not moving. Movement's velocity, so it means my velocity equals 0. The maximum height of a ball being thrown into the air occurs. This is a little physics thing, right? When you throw a ball into the air, when you reach your max height, you're at a little free standstill. Your velocity equals 0 again. So you're right there. There's a little split second where you're weightless, so it's your velocity. You're not moving, so velocity equals 0. If an object is dropped, so if your object's dropped, that means you're not like throwing it or tossing it. So that's another way of saying velocity equals 0. So when an object is dropped, that means you're just starting from a standstill, so velocity equals 0. When an object is in vertical motion, it hits the ground. So when you hit the ground, that's a position. The ground's the floor, so position equals 0. A lot of people want to say velocity equals 0. It actually has a velocity. If you think about when you throw an egg in the air, when it hits the ground, it cracks because there's a velocity to it. If there was no velocity, it wouldn't break. If asked when or at what time or how long, our answer is B. Right? So asking about what time or how long has to be time. Right? It might seem easy, but people get confused, especially when we start getting more complicated on problems. Anytime you're asking about time or how long, it's a time question. You should be solving for t. So you want to solve for t in that case. Is asked to find speed, velocity, how fast, what is the rate, or find a rate of change. That actually needs to be a velocity. Or I should probably say a rate. So, and then here's a little trick to figuring out when you're given a rate, which happens a lot now, because we're going to do rates of change. You're being given a rate when words are like per, for, or in, or use. For example, 3 pages in 10 minutes. So, right, that's 3 pages per every 10 minutes. So it's a rate. 5 miles per hour. So 5 miles per hour. Rate. 10 bananas for $3. So 10 bananas for $3. Again, these are all rates. And we want to be able to identify when we have a rate, because it helps us solve the problem, right? So rate's more velocity. It's a second derivative, not the position function. So let's move on to some actual examples, or some units and rates of change. I jumped the gun a little bit there. So these are just some units to help you understand what you're doing when you're doing it. So distance, as we all learned in like 3rd grade, it's a linear unit, right? Feet, inches, miles. It's a distance. How far are you? Area is in squared units, and volume is in cubic units. Right? Some basics. Position functions like x and xt, right? So the book and AP likes to mix these up. Sometimes they'll use xt, sometimes you use st for position. You just gotta get used to it. These are quantities. Typical examples include distance, area, volume, but they could be in units of money, people, rocks, desks, or really anything. So right, it's a quantity thing, position. So like 10 miles, right? That's a position. You're 10 miles away. It's not gonna be 10 miles per second. That makes no sense. I'm gonna have 30 people. That's a quantity, right? You want all things that have like singular amounts. By the way, singular values doesn't mean you don't have like squared or cube units. You could totally have those, right? This means you don't have a fraction. So if I say like how big is your room, you might say like 10 feet squared. That's still a quantity, right? 10 feet squared per second, then that's a rate. And they're like, wait, what are you answering? So position functions are not always position; they're just quantity functions. Position is just the easy way. We always think about motion. We think of rates of change, but really it's just any quantity. Velocity functions, or the derivative of any position function, must have units. So it's always going to have it in like a fraction. So these are going to be rates: quantity over time, feet per second, people per year, dollars per hour, rock per minute, right? It's a quantity. I'm doing this over this. We have 10 people per year. We have $100 per hour. Acceleration functions are kind of hard to think about. They're the derivative of velocity functions. So velocity functions are rate of change, right? It's a derivative, so rate of change. So if we're taking a derivative of a rate of change, then we have the rate of change of a rate of change. So it's kind of like how much is velocity increase or decrease. That's kind of a weird one. It's a rate of change of a rate of change. But when you do acceleration functions, again in quotes because they're not always acceleration, they're just like rates. It's just basically how much are you increasing or decreasing your velocity function. Now remember, it doesn't have to be a velocity. Any rate of change. So how much you're increasing or decreasing your rate of change. So these are always over time squared or second squared or hours squared. So like when you hit the acceleration on your car, it's how much faster are you going. So that's kind of the general idea. Now let's get to some examples. Example: a man is holding a ball 15 meters above the ground. He throws the ball in the air vertically, and the position of the ball is given by this equation here. So notice it's S to T is our position function, where ST is given in meters and T is given in seconds. So here's our graph. We don't always have a graph, but in this case we do because it's our first one. Here, let's talk about what we're doing, right? S is seconds. We want to label always our units. And Y is, S of T is Y, which is in meters. Alright, so notice that we start at 15. That's why I crossed right here at 15. That has a big loop. What is the height of the ball after 1 second has passed? So keep in mind, it wants the height of the ball. That's a position question. It's not saying how fast is it going or anything. That's the height. So it's position. So we're literally going to plug in 1 second, because that's what we have, into our equation right there. So we're going to do S of 1. So negative 4.9, 1 squared plus 49 times 1 plus 5. And if we add all that up, we get 54 minus 5, so 49.1. About. That's pretty dead on. And then don't forget our units, meters. I started saying after 1 second, you're 49.1 meters up, which kind of makes sense. Look at our graph here. So there's one, get about up to right there. What is the max height the ball has achieved? Now again, we got to go back to our logic here. It's like, how do we find max height? The way you find the maximum of anything actually is just we're going to take the derivative set equal to 0. Alright, we're going to let the velocity equal 0. So when you hit your max height, you're like not moving for a split second. So that's what we're going to do here. We're going to take a derivative of this and set equal to 0. So S prime of t, which equals the velocity. We're taking a derivative, so we're going to bring the 2 down, subtract 1 off. That's negative 9.8 t plus 49. Now we want to set equal to 0. Because when we hit our max height for a split second, we're not moving. Then it's just mathematics. Let's solve this. Move the 9.8 over. Divide by 9.8. If you do that, you get t equals 5. Keep in mind we found the time, so this is seconds. So 5 seconds, which actually looks like, if you look at the graph here, actually kind of looks like it. About 5 seconds. What is the maximum height of the ball? So look what they want. They want a position question, right? Again, right? Where's the ball at when it's at its maximum? So we know what the max is, or when it hits the max at 5 seconds, we just got to plug it into our position function. Because again, they're asking the position. So we're going to do S of 5. So negative 4.9 to the 5 squared plus 49 times 5 plus 5. And if we plug it into our calculator, just do some math, we get 137.5. And again, we're talking about the max height, so that's in meters. You can see the value right there. It's about where we're at, right? 137.5, so about there. So that's a first quick example of how to do a related race problem. Let's look at another one. So that last one's going up and down, so it's a vertical motion. Now we're going to go have a horizontal motion. So in this example, a particle travels along the horizontal line, and its position is given by s of t and velocity by v of t, or t is in seconds. Only select positions velocities have been given, so only selected values have been given. Let's find the average velocity from 5 to 6. Now, here's the thing. Average velocity, remember from the last video? Average velocity is the slope. If they say average, that's just the slope. So that's like the keyword. So we want to find the slope of velocity. Now here's the thing that a lot of people mess up on. If I want to find the slope of velocity, I'm actually using the position function. Right, so we have a position function graph. And you want to look at this, you're trying to find the slope of that? Well, the slope of that, right, is kind of like a derivative. And that gets to the velocity function. So when we want to find average velocity or average whatever, it's the one above it. So I'm going to actually use the position s of t2 minus s of t1 over t2 minus t1. So it's a very important concept that people tend to forget. If you want to find average velocity, use one above it, use position. If you want to find average acceleration, use one above it, use velocity. So it's tricky, I know, but that's kind of the way it goes. And then we're going to plug in our values. We're going to have 6 minus 5 over s of 6 minus s of 5. Look at our handy dandy table here to figure out what s of 6, s of 5 are. S of 6 is 1. S of 5 is negative 2. Now keep in mind, I should be doing my units. S is in feet, and then time is in seconds. So this is feet per second. That's 1 minus negative 2, so 3 over 6 minus 5 is 1 feet per second. So I get 3 feet per second is the average velocity from 5 to 6. Now that changes depending where I'm at, but between 5 and 6, average velocity is 3 feet per second. So again, it's all about using the one above it. So when we have velocity, it's the one above using position. Is it possible to find a velocity at 5.5 seconds? Explain. Now, I have 5 and 6. You might be thinking I would use IVT, but IVT won't give me exactly 5.5. So no, it can't. It's not a given value. And since it's not a given value, we could only find the average. Find the average velocity. Now the next one, find the average acceleration. Like I talked about earlier, right? If you want to find the average, that means slope. So we're just going to do a slope equation. Now the tricky thing is acceleration, so it's like, again, someone above it. So you want to do average accel. We're going to do the velocity at t2 minus the velocity at t1 over t2 minus t1. So again, it's just a normal slope equation. But since we're doing average velocity, average acceleration, is still we have to use the one above it, average velocity, or find the slope of basically the graph above it. So you just plug your stuff in. So 8 minus 2, v of 8 minus v of 2, v of 8, here's my v, is 2, v of 2 is 3. Don't forget our unit. Velocity, notice how velocity is a rate, so it's feet per second, over my time, which is also seconds. This is how we're going to get negative 1 over 6 feet per second squared. So between 2 and 8, we're actually decreasing our velocity, right? It's a negative acceleration, so we're actually going down in velocity. Is there some time when the particle is exactly 5 feet from the origin? Now, look at this question. It's a little different than the last one, right? Is it possible to find a velocity at 5.5 seconds? I don't have it. No, I can't find a velocity at 5.5. But this question is saying, is there some time when the particle is exactly 5 feet from the origin? Right? I'm not saying, could you find it? Is it possible to have a time where you're 5 feet from the origin? This sounds like an IVT question. And so for a particle traveling along a horizontal line, that means that we're continuous. Because you can't, when you're traveling, you can't just give values. So, since s of t is continuous, let's see if it is possible. Could we find a value where 5 feet has to go between? Again, notice we're talking about 5 feet. That's a position function, right? It's not a rate, it's position. So we're looking for here, and between 3 and 6, right? Since we can't skip values, if I go from 3 to 6 by IVT, I have to skip all the values in between. So between 8 and 10, f of 8 and f of 10, there's some value at supposed to be at 10. The particle will be exactly, there'll be a time where the particle is exactly 5 feet from the origin. And don't forget our IVT question, right? Remember, it just means if we have a continuous function, every value from here to here must be used. Okay, so last question here, kind of similar. Is there some time when the particle is stopped? So again, we're not trying to find the time. Is it possible that there is a time when a particle is stopped? So stop means the movement, the velocity equals 0. That's the question. Is there a time when the velocity equals 0, right? When it stops moving? So it's actually very similar to the last thing we just did, right? Can we find since it's a continuous function, can we find out when the time when the particle is 0, velocity of the particle is 0? And right here, right? When you change from negative to positive, you have to skip past 0. So likewise, since it's a continuous function, by IVT, there is some time, since you want to explain it, time between, my two values between 5 and 6, between v of 5 and v of 6, where v of whatever equals 0. So yes, by IVT, there must be some time where it crosses. Since, I could go more into like, right, since it feels formal, since v of 5 equals 1 and v of 2 equals -1, it must cross 0 at some point. But that's the general idea, right? Don't forget IVT to come back again. But that's the general idea.